guys, welcome back to part 2. This is going to cover problems 3 through 12 on the front, and then our 3 multiple choice graphing in the back. Alright, so if you missed problems 1 and 2, those are on video part 1. I had to break it up simply because I did these recordings at 2 different times, and frankly I'm too lazy to try putting them together. So if you missed it, go find it. There's problem 1, and here is problem 2. So we're now on to problem 3. Now, again, we are going to solve these in exactly the same way that we would solve any other acceleration problem. So we're going to ask ourselves, is this a horizontal acceleration or is this a vertical acceleration? Frankly, the main key is just the fact that, they gave you your acceleration right there. So it can't be a vertical acceleration, but also just by reading the problem, it's not too hard to figure out. So, first step, we write out our variables. Alright, so a car is traveling at a constant rate of 10 meters per second. The driver then accelerates at 2 meters per second squared. Hey, guess what? That's probably our acceleration. For 10 seconds. What is the final velocity of the car? So we're looking for V final. And it tells you you're driving at a constant rate of 10 meters per second. So that's going to be your initial velocity. That's the velocity you start at. It doesn't say anything about position at all, and it doesn't ask us for it, but it does tell us that this car is moving for 10 seconds. Okay, 1, 2, 3. We have enough information. So now the goal is we have to pick out the equation that best fits our information. Just for the sake of explaining in depth, our 4 equations, actually I'm just going to write 3 of them. I'll write all 4. We've got that one there. That one there, and remember these will be given to you tomorrow for the test. And finally, Vs squared equals V naught squared plus 2a delta x. Alright, so here's basically what you have to do. We'll use red for good, bad, green for good. What you have to ask yourself is your piece of information that you don't care about. And there will always be one. Now what I mean by don't care about, I mean is for that particular part. So let's say there was a part B to this that said, well, what is the total distance traveled while accelerating? We're going to care about position, just not yet. So for this particular part, to find V final, we don't care about delta x. So first step is to go through and say, okay, this equation up here has a delta x in it. So we can't use that equation. The equation below it also has that delta x there, so we can't use this equation either. Both of those are not good to use. Now, if we look over here on the right, I don't see a delta x, so that's good. First step, do I see a delta of V final? Yeah, which is great because that's what I'm looking for. Let's see, there's an acceleration, and I know that, so that's fine for both of them. There's time, and I'm given that. So that's good for both of these. And there's a V naught, which I'm also given. If I'm given all of the information from the problem, or basically there should be 3 givens you know, and an unknown you're solving for. That's how you know which equation to use. So you can use either of these. Because it's solved for V final, I'm going to go ahead and use that one there. So we have V final equals AT plus V naught. Alright, so now at this point we just plug in our variables. We have V final, as I'm clicking buttons along here. Let's go ahead and fix that. Alright, so we have V final. We're given our acceleration of 2 meters per second. We're given our time of 10. And we're given a V naught of 10. A little bit of simple mental math gives us 20 plus 10, which gives us a V final of 30 meters per second. Okay? Moving on to number 4. Jack and Jill fall off a bridge to the water below, and they hit the water 3.5 seconds later. How high is the bridge? How fast were they going when they hit the water? All right, so again, this is an acceleration problem. You can ask yourself which type. Okay, they're falling to the water below, so this should be telling you that this is an acceleration in the vertical direction. This is free fall. All right, so we're going to list out our variables again. All right, Jack and Jill fall off a bridge to the water below. Okay, it says fall off. It's not the same as drop, but it doesn't say anything about they leaped off or they jumped up and fell off the bridge or anything like that. If they just fall off the bridge, you can assume V naught equals 0. They hit the water 3.5 seconds later. Fantastic, that's going to be time. How high is the bridge? They're asking for delta x. How fast were they going when they hit the water? They're asking for V final. And because this is a free fall problem, we know our acceleration is going to be 10 meters per second squared. Now, just to illustrate what we're talking about here with the whole idea of the free response. Here, let me zoom into a slightly different area here. Let's go ahead and do it over here. All right. So if we draw a picture, we'll have just kind of a basic bridge here. There we go. My lovely artwork. All right. And we have some, we've got some water down here. All right, and then we have my incredibly fat pen. This is hard to do, but whatever, we'll live. All right, so we've got Jack and Jill there. All right, so what we know is the height of the bridge is what we're looking for. That's delta x. All right, we know they are falling downward. Now remember, for any free fall problem, we assume that the water, in this case, or the ground, the lowest point in the problem is a position of 0 meters. Okay, so since they are going from a higher position up here to a lower position, your delta x should be negative. Your velocity, likewise, should also be negative because it's heading in a negative direction. All right, this is also the same reason why gravity is negative, because gravity pulls down. Okay, all right, getting back to the problem. All right, once again, we know 1, 2, 3 things. At this point, you can find things in whatever order, using whatever equations you like, using the method we illustrated the last problem. So, let's say we find V final first. Why not? We don't have delta x, which means there are 2 equations that are possible. You can use either V final equals AT plus V naught, or you can use A equals VF minus V naught over T. It's solved equal to VF. Why not use the first one? Plug in what we know. A is negative 10. Time is 3.5. And V naught is 0, so we can safely ignore it. V final must be negative 35 meters per second. Now, a quick note. On the test for multiple choice questions, it's usually a good idea to not use the information you solved in one part for another. The reason is, on multiple choice, I don't get to see your work. So if you got part A wrong and use that information for part B, I don't know it. Okay, so I would be careful to, if possible, only use the information you're given in the problem. For example, for delta x, we have an equation that uses, V final, or that does not use V final, I'm sorry. So I would go ahead and use that one. You could use the VF squared equals V naught squared plus 2A delta x, but it's usually not the best idea. Once again, we know everything, so we plug it in. All right, V naught is 0, so this whole term can go away. 1/2 negative 10 times 3.5 squared. Now, my mental math isn't quite up to 3.5 squared, so we'll just go ahead and pull up our calculator here. 3.5 times 3.5 times negative 10 times 0.5, which is the same thing as a half. And we end up with a displacement of negative 61.25 meters. And again, like we talked about over here, it makes sense that our displacement is negative because we're starting from a higher point over here to a lower point down there. Moving on to problem number 5. All right, we once again know this is a vertical acceleration problem a free fall problem because it says downward. If it says downward, we're talking about free fall. So once again, we set up our initial variables. All right, if a ball is thrown straight downward with a velocity of 10 meters per second. Now here's the thing, we know initial velocity is going to be 10 meters per second. But what tricks people up is they just leave it that way. Because the problem only says 10 meters per second. So you see 10 meters per second and you immediately just say, all right, plug in 10, we're done. But really quick, let's go back a problem. So we were talking about with the Jack and Jill bridge. I hit the wrong one. Sorry, guys. All right, with the Jack and Jill bridge, remember, down is negative in our little free fall problem. So if we are throwing the ball downward, what that's trying to tell you, is this velocity over here, right there, that velocity is negative. That's what that downward is telling you. So you need to make this negative 10 meters per second. Off the top of the Sears Tower, 442 meters. So what that's telling you is it's falling a distance of 442 meters, and because we're falling, once again, we have to make that negative. We also said this is a free fall problem, which means we automatically know A is 10 meters per second squared. It's asking what is the velocity of the ball just before it strikes the ground. It's asking us for V final. And how long does it take to strike the ground? It's asking for time. Once again, you can solve in any order. However, I'm going to make a suggestion. It was the same suggestion I made if we discussed problem 6 from Wednesday's homework. You can solve for time first. But what that's going to involve is using the equation delta x equals v naught t plus 1/2 a t squared. Make it kind of a little smaller. All right, now there's a problem with this. We can plug in what we know. Negative 442 equals negative 10 t plus 1/2 negative 10 t squared. The problem is we have a t and we have a t squared. So how you would have to actually make this work is subtract over this 442 and set this whole equation equal to 0. So 0 equals negative 10t plus 1/2 negative 10t squared minus 442. Right there, we have a quadratic equation. Quadratic equations, not fun. Can you solve it? Absolutely. And if you're good at them, go for it. But we have another option, so why not take it? Instead of finding t first, let's go ahead and find v final. We have a single equation that does not involve time. And that's vf squared equals v naught squared plus 2a delta x. We plug in what we know. We're solving for v final. V naught is negative 10. Our acceleration is also negative 10, and delta x is negative 442. Negative 442 times negative 10 is going to give you positive 4,420. Times 2 is going to be 8,840, plus negative 10 squared gives you 8,940. Hopefully I didn't screw the mental math up. We take the square root to get rid of that squared. And once again, mental math is not my strong point with square roots. And we take the square root of that, giving us a final velocity of 94.55. Now don't forget, in front of any number after you've taken the square root, you have a plus or minus. So the question you have to ask yourself is, should this velocity be positive or should this velocity be negative? We're moving downward, which means this velocity should be negative. It should be negative 94.55, and don't forget your units, meters per second. Last step. We said to find time. Let's see, I'm running out of space here. All right, let's try blowing this section up. See if that gives us enough. Okay, apparently not. Nope. All right, we'll make do. All right, so last step. Now that we know V final, we can use this equation here. And then plug in what we know. Sorry for the messiness. I'm kind of writing on the shadow of my head over here, guys. All right, so what we have is 94.55 negative plus 10. It's basically what it winds up to, minus a negative, divided by negative 10, which gives us, okay, I think I forgot a sign there, but it should be 10.46. Let me double check my math there real quick. I think I hit decimal instead of negative. Oh, hold on, I'm gonna double check that on the calculator. This whole using a calculator through the whiteboard is just kind of ridiculous. Yeah, okay, so I'm sorry, it should be actually 8.46, not 10.46. I just did it again, didn't I? Well, here you go. Physics teacher making a fool of himself live on YouTube. So there's one answer, and there is our second answer. Sorry it's so sloppy, but hopefully as long as you're following through, you're going to get the idea. All right, number 6. Baseball player throws the ball straight up in the air with a velocity of 35 meters per second. How long is the ball in the air, and how high up into the air does the ball fly? All right, again, to save room, we're going to zoom this in. So we're going to list out our initial variables. If you don't like not having the problem to see, don't forget, you should have that sheet right in front of you. All right, so it tells us the ball is launched straight up with a velocity of 35 meters per second. So again, the question you've got to ask yourself, should this be positive or should this be negative? It says upward, which means this should stay positive. We don't know V final, at least not yet. Acceleration, because it's free fall or vertical motion, it's going to be negative 10. And it tells us, I don't think anything else, right? Nope, that is it. So throw this ball straight up in the air. All right, so here's what we have to do. We are looking for, all right, what we're looking for is our V final here. Oh, I'm sorry, not V final. Not looking for. We're looking for displacement, we're looking for time. That's what the question asks us for. Now, the trick to this problem is, again, remember, if you trace out the ball's path through the air, up at the very top, the ball's velocity must be 0 at its maximum height. So what we're going to do is go ahead and put in 0 meters per second for that. Now let me move this over so it's not stuck under the toolbar. That should be good. Perfect. All right, so that's what we know. Now, again, it doesn't matter which you find first. Just for the sake of convenience, let's go ahead and find time first. In this case, what we don't care about is delta x right there. So we use the one equation we have without delta x, or one of the two, I should say. All right, V final we know is 0, acceleration is negative 10, time is what we're searching for, and V naught is 35. We subtract over 35. Let's go ahead ahead and erase this 0 here. Now I realize it would probably be easier to just rewrite it, but hey, it's not as fun. All right, so that's negative 35. We divide by negative 10. And we'll go ahead and move that sucker over too. And what we are left with is negative 35 divided by negative 10, which gives us a time of 3.5 seconds. Again, use time as an indication of if your variables have the correct sign. If they do, time should always be positive. Because remember, negative time is just, it's nonsense. Don't worry about it. You can't go backwards in time. All right, so we know time, except, be careful, that's the time it takes to go from the bottom up to the top. So the trick is, if it takes 3.5 seconds to go up to the top, it must take 3.5 seconds to come back down, giving us a total time of 3.5 times 2, or 7 seconds. Finally, it says how high up in the air does it go? We know everything we need, but for the sake of being consistent and making sure one mistake doesn't impact us later, we're going to go ahead and use the equation that does not involve time. All right, V final is 0 squared, which doesn't matter. V naught is 35 squared plus 2 times our acceleration times delta x. So what we're going to do is we're going to square 35, which is 1225, and we're going to subtract that. 2 times negative 10 is negative 20, delta x. So we're going to go ahead and divide that negative 20 over. Which leaves us with delta x equals negative 12.25 divided by negative 20. In the calculator, you notice I ignored the negatives because they're going to cancel out anyway. And we have a maximum position of 61.25 meters. Once again, very important not to forget the units. So we have an answer here, and we have an answer here. All right, I'm going to take a break real quick, and we'll be right back. All right, let's pick back up. All right, so we are done with number 6, and we will move on to number 7. A little over, halfway through. All right, so Upton Chuck is riding the giant drop at Great America. If Upton free falls for 2.6 seconds, what will be his final velocity, and how far will he fall? You know what? Go to my teacher page and look at the in-class examples video. As I can't even write correctly. In-class examples 9, let's see, today's the 28th, I believe that's 927. We did that one in detail. It was recorded with one of my classes, so you can hear the questions and my answers to those. I think that's going to be a little bit useful, and it'll save me a little bit of time. So, YouTube video, if that already exists, go ahead and give that a look if you're having issues with this problem. Although most of us did that in class, so that shouldn't be too big of a deal. All right, we are now back to a non-free fall problem. This is a horizontal acceleration, and we know that in part because they give us, again, our acceleration, even though the units are kind of screwed up on that video, or on that, that image. So, we're going to go ahead and write out our variables. V naught, V final, A, delta x, and t. Now I'm going to grab my copy of this review because I can't see the problem. All right. Engineers designed a runway for the airport. Of the planes that will use the airport, the lowest acceleration is likely to be 3 meters per second. Guess what? There's acceleration. Or meters per second squared. The takeoff speed for each plane will be 65 meters per second. Assuming this minimum acceleration, what is the minimum allowed length for the runway? So here's where the trick is, because it doesn't specify a V naught and a V final. The only velocity it gives you is 65 meters per second. So here's what you have to imagine the situation here, if you will. You've got an airplane taking off. At takeoff, you start at rest and speed up until you're going fast enough for the plane to go up in the air. So you have to visualize that so you realize V naught has to be 0 and the 65 given has to be V final. Because we're going to start at rest and speed up to 65. All right, 1, 2, 3, we have enough information. Specifically, it's asking us for what is the minimum allowed length? In this question, it doesn't ask for time, it doesn't give it to us, we don't care. We have one equation that does not involve time. And it's that one right there. We know that V final has to be 65, and that's squared. We know that V naught has to be 0, which squared is still 0. Board's lagging a little bit. Okay. Acceleration, they say, is 3, and we are looking for delta x. So what you get here is 65 squared is 4,225 equals negative 20. I'm sorry, I have no idea where that negative 20 came from. Let's take a step back here for a second. Apparently I was thinking of a previous problem. Equals 2 times 3, which is definitely going to be 6. Delta x, we're going to do the same thing where we're going to divide that 6 over. If this thing will let me do this. So delta x is going to equal our 4225 divided by 6, or 704.17. Meters, and that's going to be our answer. Moving on, only a couple left. Number 9. All right, so this problem was also done as an in-class example, the same as the Upton Chuck. So I'm just going to write C, comment. Why is one capitalized and the other not? I don't know. That's how I roll. So go watch that video. It's an in-class discussion. It's a little bit more useful. You get to listen to me being an idiot in class like I do every day. So just like I have the links posted for timestamps for each of the problems in the comments below, I will have a link to that correct time in that video, so you can go right there. No sense in reinventing the wheel there. All right, number 10, a bullet leaves a rifle with a muzzle velocity of 521 meters per second. While accelerating through the barrel of the rifle, the bullet moves to the distance of 0.84 meters. Determine the acceleration of the bullet and assume uniform acceleration. All right, again, this one was on your homework last night. Like I said, you're going to see a lot of repeats on these review assignments. The review assignments are made up of former homework questions, which are then used to make up the test. So, again, this is acceleration, so we want to write down our initial variables. All right, now it tells us the bullet leaves the rifle with muzzle velocity of 521 meters per second. Muzzle velocity means the velocity the bullet is shot at. While accelerating through the barrel of the rifle, it moves a distance of 0.84 meters. Determine the acceleration of the bullet. Well, let me ask you this. I actually wrote something wrong there, which you might have caught on if you're actually paying attention to me doing this YouTube video. It says it leaves the barrel with a velocity of 521 meters per second. That's V final. Of course, I don't move the S. There. All right. It leaves the barrel with 521 meters per second. The velocity of a bullet just sitting, waiting to be shot, is going to be 0. So this is another one of those problems where you have to visualize the problem. It asks us for acceleration. It does not give us time. It does not ask us for time. That is our junk variable for this problem. So our one equation that does not involve time, same as the two problems go. And we plug in what we know. 521 squared, 0 squared, 2 times 0.84. 0.84 times, oh, I'm sorry, that was delta x. We're solving for a. So I'll just put it back here. It doesn't really matter. I'm having an off day apparently. All right, before we actually do the math, there should be a double check. All right, ask yourself if this is going to be a large number or a small number. And you should correctly realize that 521 squared is going to give us a pretty big number. So we're going to square 521, and then we're going to divide by all of this 2 times 0.84. So we're just going to go ahead and divide by 2, and then divide by 0.84, giving us an acceleration of a lot, 161,572. Meters per second squared. That seems like a really huge number, but it makes actually perfect sense. Simply because, well, you're going from 0 to pretty close to the speed of sound in less than a meter. It's going to be pretty fast. You're going to need quite a bit of acceleration in order to pull it off. Number 11. This is another problem off of the homework assignment due on Wednesday, so it should be familiar. We should have gone over it in class, but just in case you forgot, we're going to discuss it really quickly. Really, if you run into trouble with this, number 6, also on this video, is a very similar type of problem. But this is a free fall problem. We've got a baseball shot up into the air. It has a hang time. Determine the height it rises before it reaches its peak. Now, here's the thing. Don't get hooked up on the semantics of this. Before it reaches its peak. A lot of people are going to read that and go, okay, so you're not actually at its maximum height. No, you're at your max height. Don't worry, read too much into the, well, how much before or anything like that. It's just what is your height, or how long does it take to get to your maximum height. All right, so V naught, V final, A, delta x, and T. All right, so we know this is a vertical problem, which means that we automatically know the acceleration must be -10 meters per second squared. We know that it has a hang time of 6.25 seconds, except, remember, hang time refers to the total time in the air. So if I once again draw a little diagram of the ball's trip through the air, up here, remember, that is at its maximum height, which means time must be equal to the time it takes to go up plus the time it takes to come down. If that total time is 6.25 seconds, cut that in half. The time it takes to go up just to the top is going to be 3.125 seconds. Also up here at the very top, B final has to be 0. Because remember, if it's still moving, it's still going up or falling back down. It's only right at that instant where it stopped that it's reached its maximum height. Given that, we don't have V naught, we don't have delta x, except all we're really looking for is delta x. Here's the problem though. V naught is what we don't care about. But think back to our other equations. You know, it's been a while since we've done this, so I'm going to go ahead and draw these out again. So let's play that little game we played with a problem a little bit ago of picking the equation. So I'm going to highlight anywhere I see a V naught, because that's the variable we don't care about. It's supposed to be a V naught, not a VC. So here's the problem. Do we have an equation where we don't have V naught? So we're going to have to find V naught before we do anything else. So let's use the only equation where we don't have where we don't have displacement. Let's use one of those. In this case, it's going to be this. Vf equals AT plus V naught. V final is 0. Acceleration is -10. Time is 3.125 plus V naught. 10 times 3.125 is going to give us 31.25. If we subtract over the V naught, what that means is V naught must equal, we're just going to multiply both sides by -1, canceling out those negatives. So there's your V naught. Now that we know V naught is 31.25, we can go ahead and using that information, say, all right, so if we want to know our displacement, is going to be 31.25 times 3.125 plus 1/2 -10 3.125 squared. Plug all that into your calculator. I'm going to avoid using the in-computer calculator just because I'm going to screw it up. That calculator is awful. So as I type this into my handy-dandy little TI-83 that you should all have, what you're going to get is 48.83 meters. Now, a couple things to be careful of. First of all, double check. Does it make sense that your position is positive? It should, because we're going up into the air, and up is a positive direction. However, something to be careful of. If you screw up your signs, notice this side and this side are added. If you forgot to make this acceleration here negative, instead of plus negative half times 10 times 3.125 squared, you're going to get plus a positive. This number is going to be much, much larger here, and it shouldn't be. So be very, very careful with that. All right. That was 11. Last actual word problem, then we're on the home stretch. So let's require that a Jaguar left skid marks that were 290 meters in length, assuming that the Jaguar skidded to a stop with a constant acceleration of -3.9. Hey, right there, we're given an acceleration. Guess this has to be a horizontal problem. The other way is Jaguars generally do not go up and down unless you have a flying car. Determine the speed of the Jaguar before it began to skid. So once again, we're going to list out our variables. If this has not become a refrain running through your head by now, it should become one. Guess what? That's going to be pretty much step one for every type of problem in this class. So, it was once recorded that a Jaguar left skid marks that were 290 meters in length. Guess that's probably going to be the distance it was braking for. Assuming that it skidded to a stop, and guess what? If you're coming to a stop, V final is 0, with a constant acceleration of -3.9 meters per second squared. Determine the speed of the Jaguar before it began to skid. We're looking for V naught. We don't care about time. And in this case, unlike the last problem, we do happen to have an equation that does not include time. So, Vf is what we're looking, well, I'm sorry, that's not what we're looking for, that's 0. V naught is what we're looking for, plus 2, -3.9, plug that whole right side of the equation in. So the right-hand side we have is negative 2262. So we're going to go ahead and subtract that over. So we've got negative 2262 over here that we are going to go ahead and move over here onto the left side, which gets rid of our negative sign by subtracting it over, equals v naught squared. Take the square root to get rid of your v naught. Again, make sure we're being careful with this, because this is another double check for your sign. If you're taking the square root of a negative number, you screwed something up somewhere. So we'll multiply by -1 just to get rid of that negative sign, and we'll take the square root, giving us, move over, there we go, giving us 47.56. meters per second. Now, don't forget, when you take the square root, you have to add a positive or negative in front of it. So once again, we've got to ask ourselves the question, should it be positive or should it be negative? Well, remember, when you are slowing down, acceleration has to have an opposite sign of velocity. So if you're slowing down and your acceleration is negative, well, your velocity better be positive. So we're going to leave that as positive 47.56. All right, I'm going to take one more break real quick, and then we will finish up at the back of the page. All right, let's go ahead and finish up the rest of this review. All right, I'm going to have to zoom in here. Okay. All right, the key here, we have distance versus time graphs for the 5 objects shown below. They all have the same scale, and the question it is asking is, which object has the highest instantaneous velocity during the interval? The key point being instantaneous velocity. All right, so all of these are distance versus time graphs, but remember, what you look at on a position versus time graph to determine velocity is the slope. So you can rewrite this question as, which one, anywhere on the graph, has the steepest slope? If you look at it that way, the answer should be obvious. It's right there. Maybe you get tripped up about this graph here, because here is, looks steep, but right here, that slope is obviously the steepest. Therefore, at that point, out of all of these graphs, that one has the highest instantaneous velocity. All right, number 14. The following represents a velocity versus time graph for an object during the 5-second time interval. What you have to do is pick the acceleration. Well, remember, you look at the slope of a velocity versus time graph in order to tell the acceleration. All right, so here's what we're going to do. Actually, let me just erase all that. Here's what we're going to do. We use the magic of the Mimeo and break this graph apart. Whoa, okay, I don't know. Oh, there we go. All right, so if you notice, we have 4 distinct line segments. This line segment, remember, you look at the slope. So what we know here is that slope is down and to the right. That means that slope is negative. So what that should tell us is for these first 2 seconds right here, our slope, our acceleration graph needs to be constant and negative. Right there, what that should do is eliminate this one, because we never have acceleration graphs that look like that. It should eliminate this one, because we never have acceleration graphs that look like that. And it should eliminate this one. Because what this graph is showing is at the start, its acceleration is 0, when we know it needs to be negative. Now let's look at this line segment right there. That's a flat line segment, which means your slope is 0. So what that's telling you is in this time here, from 2 to 3 seconds, you need to have an acceleration of 0, which this graph does, and this graph does. So we're still between those two. Now we look at this line segment right here. What that should tell you is you have a positive slope. It's up and to the right. We are increasing, increasing in velocity one way or another. Okay, whether it's increasing from a negative direction, so we're slowing down, or increasing in a positive direction and speeding up. So here's what it is. If our slope is positive, our acceleration must be positive. Here we have a positive slope. Here we have a positive slope. Except, let's go back, because I screwed up and should have mentioned this before. Let's go back to this line segment here. We said that was negative, right? I'm sorry. That's positive, whereas this is negative. This one should have been eliminated after that first line segment. So what's your answer? B. All right. The following represents an acceleration graph for an object during a 5-second time interval. So once again, same thing, except in reverse. We know right here at the start, our acceleration is 0, which means right at the start, our velocity should be constant. This is constant, this is constant, this is constant, this is constant, this is constant. Now, right off the bat, some things I can probably tell you, it would be a safe bet to say those two are out. You never see a velocity versus time graph like that. And remember, on a test, I'm not trying to trick you. So you can just eliminate those straight out. All right? So now we look at the next part. We're down to 3 graphs. Right here, we have a nice, that was an interesting color. We have a nice constant negative acceleration. And remember, acceleration tells you the slope of your velocity graph. So what we need is a velocity graph that is nice and constantly negative slope. That's a nice negative slope. That's a nice negative slope. And then our only other option, hey look, the slope of that line right there is 0. B's out. All right, we look at our next section. Right here, once again, our slope is 0. So we look for a section that's got a velocity graph that's 0. And we've got here, and we have here. Both of those are still options. Last part. We have something that's positive. Well, let's see here. This goes up positive, this goes up positive, and they both come to a slight stop, just like this one does over here. So it's tricky, but here's what you've got to ask yourself. Do you accelerate more here or here? Notice, this section right here is pretty close to the axis. This section over here is pretty far away. We have a higher acceleration for a longer period of time between 1 second and 3 than we do between 4 and 5. So what that should tell you is your velocity should change more here than it does here. The answer is A. Because if you look at if you look at E over here, look at your change of velocity here compared to here. They're almost identical. Your slope should be steeper here than it is here. That's why the answer is A. Now, one other thing. Now, this isn't on your review, but I want to pull up an example and show you it real quick. like I said, I want to show you one more example, because like I told you, we're not going to have we haven't seen any multiple choice sections. We haven't seen any multiple choice graphing questions. So I do want to show you one more before we finish up. All right, this is the one I want to show you right quick. Wow, that wasn't loud and unexpected at all. All right, let me fix this real quick. All right, so what I wanted to show you real quick is something to be careful with. I know it's hard to read, but this one says, consider the following, noting the different axes. And asks which of these represents motion at a constant non-zero acceleration. You're going to get one like this on the test. So the thing to be careful of is notice this is a distance graph, this is velocity, velocity, acceleration, acceleration. So you have to be careful about these graphs being completely different. So for what's a constant non-zero acceleration, remember, if you are accelerating, your position versus times will be curves, and your velocity versus times will be nice diagonal lines. Your acceleration versus times, however, should be some nice horizontal line. So just using that, right here, we have a nice diagonal line when we're saying it should be curves. One's not an answer. For 2, we said that for velocity graphs, noting it's a velocity graph, we said it should be a nice diagonal line. 2 is an option. For number 3, we have a straight line, not a diagonal. 3's out. For acceleration, we have a diagonal, not a nice straight line. 4's out. But we do have a nice straight line for number 5. That's an option. 2 and 5 gives us the answer of, well, it's blurry, but I'm going to guess that's C. So be careful on that. When it gives you graphs like this, be very careful to note the different axes. All right, see you on Friday.